student, welcome back to one more session of analog and digital electronics. This is Vasant Nayak from Canada Engineering College. Last class we studied how to design mod 6 counter by using a JK flip-flop and T flip-flop. In this class we will see D flip-flop. In this class we will see how to design mod 6 counter using SR and T flip-flop. Before we proceed, first we'll discuss what are the difference between a synchronous counter and a synchronous counter. So students, a synchronous counter, this is the difference between a synchronous and synchronous counter. This difference, some of the differences are mentioned here, like this is very important from the exam point of view. So let us take first asynchronous counter. In asynchronous counter, flip-flops are connected in such a way that output of the first flip-flop drives the clock for the next flip-flop. That is, output of the first acts like a clock for the next one. In synchronous, all the flip-flops are driven by single clock, means all the flip-flops are connected to single clock. Now, asynchronous, all the flip-flops are not clocked simultaneously. Clock signal is given to first one, and first one will output of the first one will drive as a clock to the second. Here, all flip-flops are clocked simultaneously. What is the third difference now? Logic circuit is very simple, even for more number of states. Very simple. Here, design involves complex logic circuit as the number of states increases. The main drawback of this counter is their low speed, as the clock is propagated through a number of flip-flops before it reaches the last flip-flop. Yeah, this is also called as serial type of counter, but asynchronous counters are called as a parallel type of counter. As clock is simultaneously given to all the flip-flops, there is no problem of propagation delay. Hence, they are prepared when the number of flip-flops are very large in the design. So, the main drawback of this one is the propagation delay, asynchronous counter. The main drawback of the main advantage of the synchronous counter is like there is no problem of propagation delay. This is preferred when the number of flip-flops are larger in the given design. So this is the difference between asynchronous counter and synchronous counter. Now we will proceed to the next. So design of synchronous counter using T flip-flop. So we know T means toggle flip-flop. Now to design, you need to follow the steps. What is the first step? First step is you have to decide how many flip-flops are required. For example, mod 6. So in our case, we are going to design mod 6. So mod 6 in the sense like it should count from 0 to 5. There are total 6 states, 0 to 5. Suppose if I take 2 flip-flops, then 2 raised to power 2 is equal to, it will give 4 states. It will count 4 states. Suppose if I take 3, it will count 8 states. So what I have to do is, I can't take 2 because it will stop at 4. It will count only 4. But if I take 3 flip-flops, it will count till 8 states. So I need to stop the counter at 5, and I have to make it to loop back to the original count like 0, original state like 0. So we'll see how to do this one. So first step is decide the flip-flop. So now here in this case I have to take 3 flip-flops. So I will take 3 flip-flops in my design, that is flip-flop A, B and C. So now this is the transition table. Student, this is the transition table for T flip-flops. So first, second step is to write the transition table. Third step is to determine the second step is to write the excitation table. This is the excitation table for the T flip-flop. So excitation table indicates it's like for the state change from present state to next state, what is that input? What are the input of the T flip-flop? So now we have present state you have to write. So the present state is 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1. But the next state is for 0 state, it is first 0, 0, 0, 0, the next state is 0, 0, 1. So 0, 0, 1, 0, 1, 0, 0, 1, 0, 0, 1, 1. That is for count 2, the next state is 3. For count 3, next state is 4. Count 4, next state is 5. Count 5, next state is 0, because count 5, next state will be 0, because it will count from 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1. Totally here, you can see here, 6 states are there. So this is called as mod 6 counter, including the initial state 0, 0, 0. So when the counter reaches 1, 0, 1, next state will be 0, 0, 0. So this is very important. After that, for the other value, the next state will be don't care condition. Just put don't care condition x here. So once you complete writing transition, present state and next state, now you have to define the inputs of the T flip-flop. What are the inputs of a T flip-flop here? So inputs are TA, TB and TC. As we are using 3 flip-flops here, T flip-flops, inputs are TA, TB and TC. TA, TB and TC. Let me zoom this one. So you can see, students, here I will take the first row now. Let us take like LSB QC. You can see here QC, the present state is 0, next state is 1. So present state is 0 and next state is 1. For that, what is the transition, according to excitation table, what is the value of the T flip-flop? What is the value of input? For 0 to 1 transition, when you refer the excitation table, the value of the T flip-flop is, input of the T is 1. So input to the T flip-flop is 1. So just put here 1. Similarly, now we will take QB 0 to 0. So present state is 0, next state is 0, present state is 0, next state is 0. So here, student, present state is 0, next state is 0, the value of T is 0. So write T is equal to 0. Now you will take QA and QA plus 1, that is present state and next state. 0, 0, once again refer the table, 0, 0 transition, the value of the input should be 0. So 0. Like this, student, you have to complete all the combinations of QA, QB, QC, and you have to write, you have to define here, you have to complete the transition table by writing TA, TB, TC values. Once this is over, then you will move to the next step. Next step is you have to solve this one by using K-map. So students, here you can see we have solved this one by using 3 variable K-map. Here you can see. So after solving this one by using 3 variable K-map, we will get TA is equal to this one, TB is equal to this value, TB is equal to this value, and TC is equal to this value. Once this is done, student, then we need to write the circuit diagram. Here you can see I am taking 3 flip-flops here. All the flip-flops are driven simultaneously by clock signal. You can see all the flip-flops are driven simultaneously by clock signal. Here, students, the clock signal is either positive edge or negative edge triggered. In this case, you have taken either positive edge triggered clock. Then QA bar is the output, QB bar is the output, QC bar is the output. Then what is the value of TA? So we know, according to the expression what we got from the K-map, the TA value is this one. TA value is this one. That is this value. That is, it contains 2 AND gate and 1 OR gate. To implement this function, we need 2 AND gate and 1 OR gate. So I have taken 2 AND gate here. The corresponding input is connected, and the output of the AND gate is connected to OR gate, and output of the OR gate is connected to TA. Similarly, TB is connected in this way, and TC. See here, you have to see, student. TC is equal to 1. So TC is connected to 1. TC is connected to 1. You can connect TC bar also to, or TC is connected to 1. So once this is done, then you need to define the output. So let us write the output here. Let's write the output here. So this is the output QC, and this is QB, and this is QA. So let me mark here, this is QA, and this is QB, and this is QC, and let me write this one, this is the output. So let me write this is output, and let me represent that this in truth table also. Output is something like it starts from 0, 0, 0. 001, 010, 011, 100, 101, and after that it will loop back to 000. So this is the design of a mod 6 counter. It is a synchronous counter. Please make a note of this one. It is a synchronous counter because all the flip-flops are driven simultaneously by clock signal. So it is a synchronous counter. So this is the design of mod 6 counter. So in the next class we will see the design of mod 6 by using SR, set and reset flip-flop. Now we will see the design of a mod 6 counter using SR flip-flop as I explained earlier. So first you have to decide, first step is you have to decide how many flip-flops are required. As explained earlier, for mod 6 we need 3 flip-flops, that is 2 raised to power 3 is 8 combination, it gives 8 combination, but we need to stop at count 5, decimal count 5. So the second step, 3 flip-flops are required. The name of the flip-flop is A, B, C. Okay. Then second step in this case is like you need to draw the write the transition table. Once again, it is the same method as we explained earlier. So let me explain this one. So you need to write the present state and next state. So present state contains all the counts starting from 0, 0, 0 to 1, 1, 1. Next state is for 0, 0, 0, 1 is the next state. For 1, 2 is the next state. Plus for 2 decimal count 2, 3 is the next state. For 3, 4 is the next state. For 4, 5 is the next state. For 5, 0, 0, 0 means after 5 it will loop back to 0, 0, 0. So for 6, x, 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 that means don't care condition. 7, don't care condition. After that you need to define the inputs from the output. So inputs are SA, RA, SB, RB, SC, RC. SA, RA, SB, RB, SC, RC. So here you need to refer the transition table. So by using the transition table for SR, so excitation table, we need to use the excitation table here to complete the transition table. Let me call the excitation table from library here. So let me call the excitation table. So you know this is the excitation table for all the flip-flops. This Q indicates the present state. Q n plus 1 indicates the next state. So for the state transition from present state to next state, 0 to 0, what are the input values in case of SR, in case of JK, in case of D, in case of T? So in this case we are designing mod 6 counter by using SR. So you need to refer this and this column. So now we'll see here, so let me explain you. First we'll take Q's first row, that is LSB QC and QC plus 1. The transition is from 0 to 1. So 0 to 1, what is the value of input SC and RC, that you have to see. So for 0 to 1 transition, you have to refer the this excitation table. 0 to 1, S value is 1 and R value is 0. So here you see SC is 1 and RC is 0. Similarly QB, that is 0 to 0. 0 to 0, S value is 0, R value is X. You can see S value is 0, R value is X. Similarly, this is A, SA is 0, RA is X. Like this, you have to complete, you have to define all the inputs of the flip-flops. Once it is ready, then you have to solve this one by using K-map. So 3 variable K-map. When you solve this one by using 3 variable K-map, you will get the solution for various this one. You will get the solution for SA, SB, SC, RA, RB, RC. Here it is the expression for SA, SA and SB, SC, RA, similarly RB and RC. Once this is done, then next step is you need to draw the diagram. So here you see, students, like I am using 3 flip-flops here totally. So all the 3s are driven by same clock. is a positive triggered clock. Other than that, SA and RA is the input to the first one, SB and RB is the input to the second one, SC and RC is the input to the third one. So QA and QA bar output, QB bar, QC and QC bar is output. Let us define the output here. So this is the output. So this is the output, students. So let me write here. This is QA, this is QB, and this is QC. Other than that, input is SA, SB, SC. Similarly, RA, RB, RC. So you have to connect these gates according to the expression what you got in K-map. So this is the implementation of mod 6 counter by using SR. Now we'll proceed to the next slide. In the next slide, you see here, sometimes see like counter for other sequence. In some application, the sequence of states of the counter is not in state binary order. It is not in state binary order. For example, in some application, the sequence of counts are not in state binary order. For example, here you can see the counter starts at 0, 0, 0, then it moves to 0, 1, 0, then it moves to 1, 0, 0, then it moves to 1, 1, 0. It will skip some of the states in between. This is called as a random count. This is called as a random count. So here you need to design the counter for such type of sequences. So how to design counter for such type of sequences you will see here now. So here students, you need to design now the counter for these sequences. Like it should start with 0, 0, 0, 1, 0, 0, then it should jump to 1, 0, 0, 1, 1, 1, 0, 1, 0 and 0, 1, 1. That means in between some of the states are skipped. So this is the present state and this is the next state. So now wherever the skipped state, you need to mark X, 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 that is you need to mark don't care condition. So we'll see how this works exactly. So now students, you see here. So initially, to write the next state here, first you have to see here 0, 0, 0, you have to refer the state graph. What is the next state for 0, 0, 0? 1, 0, 0 is the next state. 0, 0, 1, there is no next state is defined. That's why you can write like, you can write X, X and X. 0, 1, 0, 0, 1, 0, what is 0, 1, 0? 0, 1, 0 is here. What is the next state? 0, 1, 1. 0, 1, 1, 0, 1, 1, what is the next state? 0, 0, 0. 1, 0, 0, what is the next state? 1, 0, 0, 1, 1, 1. 1, 0, 1, there is no state is defined for this one. This one you can treat as a don't care condition. This one you treat as a don't care condition. 1, 1, 1, 1, 1, 1 is a 0, 1, 0. Like this you have to complete the present state and next state table. Then you have to complete the transition table. So to complete the transition table, here this is the transition table students, present state and next state, and you have to, as I said, you have to consider those input with the incomplete inputs of present state and next state as X, 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 that is don't care condition, and this is the value of TC, TB, TA. By referring the excitation table, you have to fill the value of TC, TB, TA. I have covered this in earlier video also. So now we'll see here you have to solve this one by using K-map. So this is the K-map representation, and you have to solve this one by using K-map, and you will get the value for TC, TB, TA. Then same can be represented in circuit diagram. So you can follow the circuit diagram here. So 3 flip-flops and all the flip-flops are connected to clock cycle, and TC, TB and TA value and output value you have to represent. So this is the way you will design counter for other sequences. So now we'll see the next one. Here also, sometimes you need to design the counter, self-correcting counter. Self-correcting counter means in the above design here, it starts from 0, 0, 0, 1, 0, 0, it moves to 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 0, 1, 1. But like in between, if it skips, suppose the counter starts at 1, 1, 0, then the counter will in locked state, it doesn't know to which state it has to move. So you need to correct this one by this type of counters are called as self-correcting counter. For example, if the counter started at 1, 0, 1, 1, 0, then it will move to 1, 1, 1, 1. If the counter starts at 0, 0, 1, it moves to 1, 1, 1. If the counter starts at 1, 0, 1, it moves to 1, 1, 1. This is called as a self-correcting counter. So we will see the next slide. So now the design of D flip-flop. The design of D flip-flop here. So as I explained earlier, the design concept, this design concept is also same. So you have to refer the actually graph here. The design concept is same.